Our next topic is going to be on gravitational field strength. So before we were talking about gravitational force, this is slightly different. So now we're going to be talking about gravitational fields. So a gravitational force, which we talked about before, we can call an action at a distance force. An action at a distance force. That's a fancy way of saying that this means it's a non-contact force. It's a force that can accelerate another object without touching it, or accelerate a force. If you think about it, this is like gravity. It still pulls me down to the ground, or if I drop a ball, it still pulls the ball down to the ground without actually touching it. It's not pushing or pulling directly. So if we have a field is a model that describes a three-dimensional region of influence to an action at a distance force. It is represented by vectors or field lines. So vectors are just a fancy way, again, of saying arrows. They're lines with arrows on them pointing in the direction of the field. The field is always going to be stronger when the vectors are closer together. It can be attractive or repulsive. So in our case, when we're talking about gravitational force, that means it's only attractive. Gravity is never going to push two objects away. It's always going to pull them together. Where it may pull them away is if you have an electric or magnetic force. Electric and magnetic forces, they are going to be attractive or repulsive. If you think about it, that's kind of like when you're using magnets. If you use the one end of the magnet, it pushes together. But if you flip the magnet over, then they repel each other. They're repulsive. Alright, so that is the three different types of action to different forces we have in physics. But the one we're going to focus on is gravitational force. So with that, we can use a test object to determine the magnitude and direction of the field. So what a test object is, it's something that is small, that feels the force but doesn't have a field of its own. So it's a small something, not necessarily an object, that feels the force but doesn't have a field of its own. It's almost like an imaginary or make-believe object somewhere. So if we take a step back here, we can look at what the gravitational field might look like. So for example, if I draw the Earth, remember, has a force of gravity that pulls everything towards it. It's actually a 360-degree pull. This is because the Earth is spherical. It is not a flat surface, despite what some people say on the internet. Alright, it is going to have the strongest pull closer to the surface. So it's strongest. Here you can see that the field lines are very close together. Relative to out here, where they're much further apart, that's going to be weaker out there. Alright, it's weakest further away, strongest closer to. So if the Earth on its surface we know has a gravitational constant of 9.81 meters per second squared. As we get away from the surface, its gravity is actually going to be less than 9.81 meters per second squared. So everything we've done before has been on the surface or so close to the surface that it doesn't matter. But as we get further away, this number is not going to stay the same. what we were talking about before with test objects is, so if I take maybe a person there and use them as my test object, they're going to feel the force due to gravity, but they are so much smaller that we don't include their force due to gravity pulling the Earth towards them. So I might have an object that far away, I might have it way far away, I might have a test object right on the surface. Again, all this test object does is just tells us at that point what the gravitational field strength is like. It is not pulling its own gravitational field strength. It's the same thing when we have a smaller celestial body. So maybe we're using the moon. This is the moon. The moon is going to have the same thing. It's going to have a different force due to gravity, but it's going to have a much smaller force due to gravity than the Earth because it has a much smaller mass. Everything's still going to be pulled to it in every direction, but a much smaller mass. Without getting too much depth into it, the moon's gravitational pull is why we have tides or why we get such massive waves in the ocean. It's what's actually pulling the waves towards it. Very simply explained. So again, in gravitational field, it's attractive only. The field lines always point towards the object creating the field. These lines always go in the direction of how it's going to be pulled. It has infinite range, so it can go on for as far as we can imagine. The test mass will be will accelerate towards the object at a rate equal to the acceleration due to gravity at that location. And G is also known as the gravitational field strength, measured in newtons kilograms. So like before, I said now that it might not be in meters per second squared. It might be in newtons kilograms. That's because the gravitational field strength is going to change as you get further away. So we have a formula if we are using the mass of our test object. Our formula, again, we've already seen about 20 times, but it's G is equal to Fg over m. We often write it as force due to gravity is equal to acceleration due to gravity, mass times we often rate it as force due to gravity is equal to mass times acceleration due to gravity. But remember, this G now doesn't necessarily represent mass or acceleration due to gravity. It represents the gravitational field strength. Alright, so acceleration due to gravity, when we had that was measured in meters per second squared. Gravitational field strength is measured in newtons kilograms. So if we use this information to solve an example, we have an 80 kilogram astronaut that weighs 303 newtons on planet X. Remember, his weight is the force due to gravity on planet X. Alright, we want to figure out what is the gravitational field strength on the surface of planet X. So gravitational field strength, again, is G. However, we are now on planet X. We're no longer on Earth, so it might be 9.81, but we don't know that for sure. It might be something completely different. So right now, that's what we want to solve. Like the question says, our force due to gravity is 303 newtons, and the astronaut has a mass of 80 kilograms. So using our formula, G is equal to Fg over m. We have our force due to gravity of 303 newtons, and the mass of the astronaut is 80 kilograms. That's going to give us a 3.8 Newton per kilogram gravitational field strength. It's also a vector, and we know it's going to pull towards the surface. So we can go, it's on the surface, so relatively we can write down as a direction. So go ahead and try this below. Try with the different gravitational field strengths on the different surfaces what your weight would be, not your mass. So you're going to use your mass in kilograms, not pounds, to find your weight on the different planets. So that's what we would do if we were given the test mass. When we are not given the test, for example, if we have the Earth pulling on a test object, if we're given the mass of the Earth or the planet, then we would use our source mass formula. Our source mass formula is on your formula sheet as well. That is G is equal to capital G, M1 over R. M is the mass of the source planet, moon, star, etc. in kilograms. R is the distance from the center of the planet. And G is our gravitational constant. It's 6.67 times 10 to the negative 11 Newton. If we look at an example, we wanted to determine the gravitational field at point P, which is 25 meters away from a 50 kilogram mass as shown in the diagram below. If we are drawing our field strength, remember our arrows are towards the gravitational field or the gravitational pull. And in this case, that's going to be towards the mass. So this mass has a mass of 50 kilograms. And it also is a distance 5 meters away from our point. So to solve for this, to solve for our gravitational constant, which is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times our mass, which our source mass is 50 kilograms, and that's divided by the distance away. So the radius is 25.0 meters squared. When you plug that all in, you're going to give an answer of 5 to the negative 12 newtons kilogram. In our picture, again, this is a vector, so we need a direction. This point is going to be pulled towards the object, so it's going In the next example, it wants us to calculate the gravitational field strength on the surface of Jupiter. For this, I'm going to give you some information that's not given in the question. If you were given a question like this, you would be given this information as well. So the mass of Jupiter is 1.9 times 10 to the 27 kilograms. It also has a radius, or the distance from the center of the planet is 7.15. We want to find what is its gravitational field strength. So in the mass of the source, which in this case is Jupiter, using this, we're going to plug in what we know. G is a gravitational constant, 7 kilograms. The distance from the center of the planet to the surface is 7.15 times 10 to the 7 meters. So we are going to get a gravitational field strength of 24 newtons per kilogram. We didn't draw a picture, but remember, when you're on the surface, relative, it's going to seem like you're being pulled down. So our direction is down.